Hello and welcome everyone to today's webinar. My name is Sébastien Vermeulen and I'm joined with my colleague Benoît Gantier.
Hello, everybody.
Both Benoît and I work for the Sarrazin pressure relief valve line at Trillium Flow Technology. Really, we want to thank you for taking time to attend from your busy schedule today. Benoît and I are excited to present today's topic, some fundamentals about PRV sizing and selection, and how it can help you to reduce your TCO getting out API. Well, after a brief introduction of both of us and Trillium entity, we will detail the applicable part and section of this standard and code applicable for PRVs. We will allow you to get a better understanding of pro and cons of API. Then Benoit will explain how to pass the National Board Product Certification. To finish, we will close this webinar by our traditional Q&A session. So if you can ask the question how they come up, any Q&A will be at the end of this presentation to be more efficient. Remember to keep presentation in a full screen mode, if possible, to see data presented in graph and table. Throughout today's presentation, there will be some QR code available to scan to learn more about our contents. For example, this one will give you a direct access to the LinkedIn page. So my name is Sébastien Vermeulen. I hold a master's degree in fine element analysis and joined PRV industry in 2009. I became familiar with the ASME code during 5 years in the engineering department with Emerson before joining Trillium, its product team, and being focused on the Sarrazin pressure relief valve line.
Hello, I'm Benoît Gantier. Thank you to attend this webinar. I entered the valve industry more than 10 years ago now, right after being graduated from mechanical engineering. Today, I'm based in North of France facility, and I'm in charge of designing the new Sarrazin RSBD products, which is a brand of the Trillium Flow Technology Group.
So a quick overview of Trillium Flow Technology brand portfolio before going more in detail about API. We have a lot of content today, so we'll try to make it brief. Trillium design and manufacture mission critical valve and pumps and provide aftermarket part and service for the global power generation, industrial, water and wastewater, oil and gas, and other aftermarket oriented process industry. As you can see, there is a 17 long-standing trusted brand dated back 165 plus years experience, recognized globally, serving you as a customer from our 11 manufacturing facility and 4 service center localized throughout the world, the US, the UK, France, Italy, Netherlands, South Korea, China, and India. In total, it represents 2,000 employees worldwide with this objective to reach 1 billion in the next 5 years. Trillium Flow Technology has a long heritage of innovation spanning 190 years. We are continuously adding new products and service to make your process more efficient and productive. Let's take a few about Sarrazin, some most important dates. So Sarrazin celebrates a 175 years experience this year. In 1948, the company has been created. Mr. Descamps created a forge mill. Then in 1956, we manufacture our first spring-loaded pressure relief valve in accordance with ASME standard. Our first customer has been Total Energy now. So yes, there is a kind of a French synergy. In 1983, Sarrazin was sold to the US company Anderson and Greenwood, who were the leading global manufacturer of pilot-operated relief valve. It is at this period Sarrazin & Co. Became Atco Sarrazin and manufactured the Atco pilot-operated pressure relief valve. Another date is in 2013, because we target a new market, the power market, manufacturing the first ASME safety valve. It's not the topic of the day, but it was also an important date for Sarrazin. So Trillium probably doesn't ring you the bell because it's a new brand, a new group, a name that has been created in 2019. Sarrazin was part of VIII before, during 20 years, from 1998 to 2018, before joining Trillium, before creating Trillium. So it's all the same brand, but under a new group name. We make the acquisition of Red Point in 2020, mission critical valve, and more recently, thermomechanical pompe, who joined the family in 2021. So let's detail now the applicable part and section of this standard and code applicable for PRV. So this is to give you a global overview of the difference between API and ASME, a comprehensive view before going more in detail. So in comparison with ASME, the API standards are not mandatory by law and are primarily used in the oil and gas industry. That is to say, oil refinery, petrochemical facility, gas plant, liquefied natural gas, LNG. ASME 1 is not within the scope of API. API is intended to be supplement, but not supersede the ASME regulation. They are recognized guidelines, and most of customers may mandate compliance since API standard may be incorporated in the specification as a reference. Basically, we can say 100% of US EPC require a PRV that comply with API standard. Some other country simply ignore it. There is 100, I wouldn't say 1,000, but there is 100 API publication. Of course, during this webinar, we will only be focused on those who has a direct impact on pressure valves. In total, there is 4 major ones. So API standard 520, which is split in 2 separate parts. The first part for the sizing, the second part for the installation. API standard 521, which gives us estimation of the noise level from the point of discharge to the atmosphere. At this point, it is interesting to note some customers ask us to apply different kind of applicable code, like the VDMA, a German standard used for control valve to calculate the sound power level within the pipe. But yeah, there is different kind of standard, but at the end of the day, PRV is a normally closed device, and there is no significant room of reduction regarding the noise level. So it's something we tend to deviate. About API standard 526, it will give you many valve center to phase dimensions. Probably it's the most important one because it gives center to phase dimension, but also recommended inlet and outlet flange pressure limit at a certain temperature for a certain material. We will go in detail just after. And then the standard 527, that will be explained by Benoit, which is more in the operational side to perform a leak tightness test. On the opposite, on the right hand, you have the ASME boiler pressure vessel code, which is mandatory by law. It is largely mandatory in US, but not only. The US code is similar to European PED, the Pressure Equipment Directive. Customers across the world may impose suppliers to follow them, even if it is not mandated by law. Today, there is 13 sections. The last section has been added recently to incorporate PRV. So first, it was section 1. ASME has been created starting by the steam fire pressure vessel for power application to protect the steam boiler. It was quite normal. The section 2 address material, outline the material that should be used. Section 3 is also a logic. The next is logically the next one, because nuclear or power station, the NV stamp is also a part of power. It's a particularity with irradiation, but it's a power segment. It is mainly used, it is only used in US, meaning it is not mandated in other parts of the world. Section 5 is ND requirement and testing. And Section 8, so Section 8, by the past, the pressure valve requirements were centralized in ASME Section 8. But from 2021, ASME created an additional section, the ASME Section 13, where this requirement has been now transferred. So if ASME Section 8 continue to provide the acceptable methods and requirements for overpressure protection for unfired vessel, the UV stamp, ASME Section 13 go through now into the requirement of safety valve, including a rupture disc. Of course, there is other section around railing and brazing. We don't expect you to know all of these, but by heart, of course. But we want to reiterate the importance of them as far as the regulation. So let's move on API now. Let's highlight together some pros and cons of API. So we are going to draw your attention on some essential notes into the API standard we think it is important you are aware of. The first part in the API standard 520, part 1. It contains formula for the proper sizing and selection of safety valve and rupture disc for vapor, gas, liquid, or two-phase fluid. It also gives guidance for preliminary sizing and effective flow coefficient. That's very important, which is a relative measure of a device efficiency for allowing fluid to flow regardless any specific valve design. So in API, we consider, in a nutshell, if you have a perfect nozzle with a fixed diameter or like a ball valve, and its flow 100% through it with no reduction or inefficiency, it will have a coefficient of 1. That number begin to drop, if there are any inefficiency. In API, the coefficient benchmark used include gas, which is equal to 0.975, liquid, which is equal to 0.65 because it's more viscous, and the two-phase, which is equal to 0.85. This coefficient can be used as a general guideline to support you performing a preliminary sizing that is roughly in line with our safety valve relieving capacity. Part 1 also provides curve for back pressure, so curve chart for coefficient factor or other things that can affect the flow rate of the valve. Part 2 of the 520 deal with installation. There is standard that recommend reducing inlet line loss under 3%. Otherwise, the valve's capacity reduction cannot be neglected. Recommendations are mainly provided to avoid valve shattering or fluttering due to installation flow. To be, for example, be as close as possible to the pressure source, get a nominal inlet pipe diameter higher than the valve inlet nozzle. There is also guidance on where to put piping support and how you should bend on the outlet discharge piping to prevent build-up back pressure, for example. So another standard is API standard 526. Again, probably the most important one as it is a purchasing standard. In API, as it is mentioned, the chart here shows different designation of the different orifices and the valve nozzle. In total, there is 14 orifices from D to T and the associated standard area through API. It is worth mentioning that we can propose smaller or bigger orifice. Thermal expansion valve will be out because the orifice is smaller. Orifice V and WV for star flow can be also proposed, but it will be out of API. Also, this will give you the different inside and outside diameter size and class configuration that are available by pressure relief valve type. In this example, we have a 4x6 N orifice for spring-loaded that can go up the 900 class. It's also, there are center to phase dimension associated one with this valve. The center to phase dimension are split out by spring-loaded and pilot-operated valve, like for the class. For example, if a competitor has a spring-loaded valve out in the field that is a 4x6, our valve will also meet those same inside and outside dimension, since it follows API standard 526. So most US manufacturers are meeting this standard. When you get into thermal expansion valve, like the 9 series, not all of them match with the A and B dimension. So a handful of competitors try to match each other so that end user can easily swap out when they need replacement. But it's not the most important cost when you have to adapt a safety valve. It's not the safety valve itself, it's any piping modes, any piping modification. So it's very complicated to adapt the center to phase dimension of center to the safety valve. And that's the reason there are some crafty competitors that have a solid install base where the A and B dimension do not exactly match. And on that case, it's harder to replace. In API, we have also a limited number of material selection: carbon steel, stainless steel, nickel alloy, Monel, so basically WCC, CF8M, WC6, M35.1, and CN7M. It's more extended in ASME. We will see that just after. Here you have a brief comparison of the pressure and temperature limit we can find in API, the 4x6 orifice spring-loaded type versus pallet operated in the bottom of the screen. So each material has its own pressure limit depending on the temperature. But it is interesting to note most of these pressure limits are coming from ASME B16.34, unless certain supplement exceptions, the one under bracket, as you can see on the screen for the 600 and 900 for spring-loaded type, where the restriction is coming from the spring itself. So obviously here we can see the pilot offer a higher pressure temperature limit, which is one of the key benefits of pilots. So the takeaway is API give you effective orifice. The 0.11 inch for the orifice, inch square for the orifice D will be the same if you consider Trillium or any competitor, and if you ask us to quote in accordance with API. So combined with the API 520, you should have all necessary data needed to make a preliminary sizing. This will give you a general idea of the scope of valve you need and the size you need. This said, the effective orifice area and the effective coefficient of discharge should not be used for the final PRV selection, and we will see just this later. So don't drop off the webinar immediately. Don't be afraid by this formula. We just try to select the most simple one. And the takeaway here is just to review the sizing equation for vapor and gas and how they differ between the API code and the ASME code. Basically, this is all the information we want from you to determine the size of the valve. Without this, it will be difficult to determine the proper size and selection. So we have some basic, the required flow rate, the type of fluid. It's interesting to note we also consider the P1, the relieving pressure at the relieving capacity, which is used for the calculation. It's not really the set pressure, which only occurs for a limited period. Both formula are essentially the same, as we can see, except the coefficient of discharge. The ASME is going to use the actual derated flow coefficient that has been tested by the ASME National Board laboratory testing and explained by Benoit in a few minutes, versus the API, which is going to use the effective coefficient that we just present in the previous slide. So the result, of course, should be met or exceed either the effective orifice area for API or the actual orifice area for the ASME. The mixed is completely forbidden. In no case, an actual orifice area should be used in conjunction with an effective coefficient of discharge for calculating the capacity of the PRV, for example. Again, we reiterate, for more accurate selection, you have to consider individual valve manufacturer design, implement the actual orifice area and certified coefficient of discharge of the valve, and verify the rated capacity of the selected valve meet or exceed the required capacity. Just to give you some color on that, we take an example. So API, it will be an API calculation. So here we have a gas sizing. Customer asks for 300 kilogram per hour. The gas is a natural gas, so we can find the basic data we need, molecular weight, CPCV, compressible factor, the set pressure and the relieving. We put that on the calculation box, the one we just explained before. Of course, In case, of course, in Trillium, we have dedicated software to do the job. And at the end, the most important is we collect the calculated area. So in that case, the calculated area is 11.74 inch square. If you take a look on the graph, you have in blue the spring-loaded type, in green the pilot-operated type. So we see immediately the capability to pilot to operate at a higher pressure limit. This said, if I need to select an orifice, I need to select the next upper orifice. So for that, I need to go with the R orifice, whose sizing is 16 inch square. It's okay, but we can see also for spring-loaded, the R orifice is limited in terms of pressure. It can only go up to a 300 psi, the API version, the casted body. And if I need to select the orifice that can withstand such kind of pressure, the set pressure is equal to 1020 psi, I need to go on an M orifice. And I will have to go on an M orifice. The only issue is now my section area doesn't exceed the required one. So I need to duplicate to adopt a multiple valve selection. Exactly, if I divide my required area by my section area, I will find 3.5. So I need to go on 4 M orifice, 4 quantity of spring-loaded M orifice to meet the customer requirement, to meet this scenario. It's a lot. Obviously, it's not only the only version we can propose. There is different kind of technology. Pilot can withstand higher pressure. And on that case, I can adopt a pilot. So the R orifice, one single pilot. So it's a one of benefit of pilot to reduce the valve quantity to be able to operate on higher pressure. So I will take over, I will hand over Benoit. That will also explain the difference if we adopt the ASME sizing now.
Yes, thank you, Sébastien. In this second example, we will compare API and ASME sizing. So on the table, you can see here in the left column, there is API standard coefficients. They are not specific to any manufacturer. They are the same for everybody. And you can note also that the discharge coefficients for spring-loaded valves are the same than for pilot-operated valves. On the right column, you will have the ASME data. They are the actual manufacturer coefficients and discharge areas. They are specific to the specific design or the specific product range. The discharge coefficients are based on real tests that are performed on ASME representative laboratories. For example, the national board, as Sébastien said earlier, they are based in Ohio. On one hand, if you look at the calculated required discharge area, API requires 18.83. The discharge areas are given in square centimeters here. It isn't changed regardless of the product type, either spring-loaded or pilot-operated, as the discharge coefficients are the same. Competitors will have the same orifice selected, here an API orifice M. API provides preliminary sizing that can be used to prepare, for example, a purchasing specification without considering any specific design or manufacturer. Now, when you use ASME rules, the required discharge area is 20.96 for spring-loaded valve, for our spring-loaded valve, and 20.91 for our pilot-operated valve. You may also have noticed that the result is higher than the required API discharge area, since ASME calculations includes a safety discharge coefficient of 0.9. So they are around 10% higher. Now, when you look at the actual discharge area of our spring-loaded valve, our L orifice have a 21.19 discharge area compared to the 18.41 for the API L orifice. We have seen previously that an API M orifice was required with API sizing. The actual discharge area are much larger on our valves than on the minimum discharge area required by API. So we can recommend to use our L orifice for this specific case. To summarize these table results, API valve sizing will be a preliminary sizing identical for all manufacturers, but for ASME sizing, it will integrate the valve design specificities, such as maximum set pressure, as Sébastien showed previously in the previous case study, the specific discharge areas, and the allowable back pressure, for example. And it will be different for all manufacturers. When we receive preliminary API sizings from our customers, we will compute it in our internal ASME sizing program in order to confirm the proper valve selection, including our design specificities. On this example, we are talking about only one orifice difference between API and ASME sizing with the same valve size. Most of the time, a lower orifice will allow the user to downsize the valve, and it will induce cost reduction, mostly when you have to consider thousands of similar cases in a complete plant without considering potential issues that can be generated due to valve oversizing. Valve oversizing can lead to chattering or fluttering, for example, which can quickly erode the parts or disassemble some bolting flange, for example. Later on this webinar, we will talk about our new pilot-operated valve range, the 78 full bore, that can bring even more cost savings. Now, we'll talk about the next standard 527, that deals with seat tightness for safety valves. This standard applies for the three kinds of test reed commonly used in our facilities to adjust the valve set pressure. So we use air, we can use water, and we can use steam, depending on which fluid the valve will see in service. The configuration shown on the screen is called a Kellogg test. It is used to quantify the seat leakage of a valve operating on gas. Test operator plugs the valve outlet with a blind flange or a rubber plug. A tube crosses this flange or plug and brings the seat leakage into a water bottle. The seat leakage is channeled below the water level. The pressure at the valve inlet is then raised at 90% of the set pressure so that the valve remains closed, and test operators count the number of bubbles created by the seat leakage for 1 minute. So it's a visual indication of the seat leakage. We'll dig in details on the next slide, the allowed air leakage rates per orifice. For valves operating on liquid, the valve outlet is filled with water above the seat contact, and further leakage is collected during 1 minute. So you can have the total leakage per minute of the valve. For valves operating on steam, the outlet is inspected on a black background so that you can visually see the steam leakage. And also audible leakage are considered non-acceptable for the valve. As said before, for valves tested with air, the maximum seat leakage in bubbles per minute for a metal-seated valve will vary depending on pressure, orifice, and size, on design pressure and size, and orifice size. Sorry. As you can see, for a D through F orifice, so the small valves, the maximum seat leakage at low pressure is 40 bubbles per minute. And as you go up in set pressure, that threshold increases to reach 100 bubbles per minute. For bigger valves, you're allowed for 20 bubbles per minute at low pressure, and the same criteria applies as you reach higher pressures. Those criteria on API standard 527 are the same for spring-loaded and pilot-operated valves. We mentioned Trillium is used to comply with the most stringent criteria that also comes from customer requirement. Customers like Shell or Air Liquide, for example, and many others, have their own tightness criteria that can supersede API standard 527 and can require, for example, helium fugitive tests or leakage tests under cryogenic conditions, for example. When tightness is important, when dealing with a high value or very dangerous media, or if the user wants to operate the safety valve very close to the set pressure, for example, in power applications, pilot-operated valve can be a good option. Here are shown the graphs of the force that acts on the disc as pressure increases. The left graph is for spring-loaded, and the white graph is for pilot operated valves. On spring-loaded valves, the load applied on the disc decreases with the increase of pressure. There is force equilibrium at the set pressure, so no force is acting downwards at the set pressure. At API standards 527 seat leakage test pressure, so as a reminder, it's 90% of the set pressure, only 10% of the spring force remains on the disc to ensure tightness. On contrary, on pilot-operated valves, the inlet pressure is directly on the valve piston, which has a higher tightness area than the disc. This difference in area ensures a greater sealing force along with the pressure increase. At 90% of the set pressure for the seat leakage test, nearly all the available load is applied on the disc. This is why pilot-operated valve must be considered when tightness is an important criteria or when the user wants to operate the process close to the limits. Here you can see that Trillium exceeds the API standard 527 requirement for pilot-operated valves because as standard, Trillium checks the seat tightness also at different set pressures as a standard practice at 5, 30, 50, and 90% of the set pressure to ensure that the valve is tight even at low pressure.
Thanks. So let's go into ASME code now. Code regulation for on-fire vessel. We'll talk mainly about Section 8 and associated national board product certification. But before starting, we want just to talk a few about ASME 1. It's not part of the presentation. It's just parenthesis, just to give you some tests, some color regarding the different ASME requirements. ASME 1 is completely different. The valve is able to operate in a very, very short pressure range. It's a snap action valve with a lot of stream to guarantee such kind of performance. If in oil and gas industry, the main criteria are coming from finally the material selection because we are dealing with corrosive application. In ASME 1, steam is steam, so material selection is not so critical. It's a carbon steel, but on the opposite, the parameter is very, very important because the steam is a money maker, and when the valve is leaking, it's a disaster. So the graph has been simplified and the table has been simplified for the need of this presentation, but regardless of the line considered here, you can see how ASME 1 criteria are more stringent than the ASME 13 criteria at any level. So if you consider, for example, the set pressure, the value at which the valve is supposed to be open, the set pressure tolerance is only plus or minus 1% versus 3% for ASME 1. ASME 8, ASME 14, sorry. Regarding the overpressure, so the overpressure is when the pressure increase over the valve set pressure, it's only 3% versus 10% for a normal operation for ASME 13. The blowdown, if you consider now the blowdown, so it's the opposite. It's the difference between the set pressure and the resetting pressure. It's between 2 and 4% for ASME 1 versus 7% when you have an adjustable blowdown. Otherwise, it is just noted and recorded for liquid application mainly. It's completely, it's much more larger. It's really interesting to note finally minimum blowdown also is required because sometimes you can have some bad marketing information mentioning pilot operated valve pop action can have a 0% blowdown, but it's not really the right way to proceed because if you have 0% blowdown, you have a high risk of shattering issue. So, and the seat tightness. So the seat tightness is a pure performance because in that case you reach 96% of the set pressure. It's as close and as efficient as a pilot operated valve. Pilot can be tight up to 98%. And here, thanks to the engineering work, thanks to the design of the disc, we managed to have to reach 96% of the set pressure, which is excellent compared to the 90% of the set pressure expected from ASME 13, and that's the reason why we check it the seat tightness at 90% in accordance with API standard 527. So it's really impressive. So let's back to the ASME section 8 now. So first, we want to differentiate between these two groups, because in ASME, there is two separate groups. The ASME group creates the rules for constriction, for pressure vessel, and the regulation around how you should manufacture and test a pressure valve. And on the opposite, you have the National Board of Boiler and Pressure Vessel Inspector that enforce the law that has been created by the ASME. So the ASME is the law, and the National Board are the cops or the inspector. They are assessing the valve and whether it complies with the code in place. As soon as the valve is ASME stamp, it can be in US, but it can also be worldwide. If customer in Middle East ask a valve which is a UV stamp, you need to comply with ASME requirement. Otherwise, you can lose your stamp, and it would be a drama on that case. So the scope of the section 13 valve is only going to apply for valve which with a set pressure of 15 psi and over. Under this value, it's simply out of API. For PED, it's a 0.5 bar. But how the most important is to make sure the valve relieve the right capacity. The valve is first it's a safety valve. You need to protect the people and equipment. So you need to be open at set pressure. You need to release the capacity. You need to guarantee the valve efficiency. The valve efficiency is mainly based on the derivative coefficient factor, how we can get it, how we can guarantee it. Again, on that case, I hand over Benoit to talk about the National Board product certification.
Yes. When you order a UV or V stamp valve, you are ensured that the valve design has been tested by an ASME representative and that quality of the valve will be ensured. In order to be able to stamp a valve, our company must demonstrate an ASME compliant quality system first, which is periodically audited and hold a valid product certificate. So I will now talk about the detail of how we can get this product certificate. When considering a complete valve range, like our latest 78 full bore, for example, the preliminary certification consists in manufacturing 9 test valves, so 3 different sizes at 3 different set pressure. It makes 9 valves by the required fluid type. So you have one certification for compressible fluids and one for certification for incompressible fluids, water, for example. Those 9 valves are set in our facility, and they are then shipped to the National Board in the US for testing. All valves are then tested for proper operation first. So the criteria that are inspected are the set pressure, the lift at overpressure, the stability when discharging, the blowdown, and the seat tightness. And then the valves are tested for flow coefficient in order to establish the discharge coefficient. Back in the initial certification, all valves whose operation parameters are outside the tolerances are rejected, and 2 spare valves must be provided for compensation. Discharge coefficients are then computed, and they shall fall into a plus or minus 5% range over the mean discharge coefficient. Here is the graph showing the 9 discharge coefficient of the preliminary 78 full bore certification. The average discharge coefficient was established at 0.791. Any test valve discharge coefficient that deviates more or less than 5% from the average will be rejected. So here we can see that one valve was discharging too much, and it has been rejected at the first try. After orifice modification and test of the new configuration, all 9 valves discharge coefficient falls into the plus or minus 5% tolerance, and the valve design is preliminarily qualified. After preliminary certification, where prototypes were allowed, ASME requires a production certification, which requires to manufacture at least 2 production valves, and prototypes are no more allowed. Those valves are inspected in our facility by national board inspectors. Then we ship it back into the US for complete test, for operation and flow capacity. If those tests are compliant, we have the right to stamp the valves. And after the production certification, the actual coefficient of discharge of the safety valve range is published into the National Board Red Book, which is accessible by anyone, either on the internet, or I think you can order it directly on the website. Those production certification are looked every 6 years in order to ensure our facility have consistency in manufacturing those valves. So every 6 years, we need to manufacture 2 production valves and to ship them into the national board for test. Here, Sébastien will show you an extract of the Red Book for this safety valve range, the 78 full bore. You can see in the denial name on top of the table, and you will have the certified value, the discharge coefficient value that is certified, that will be shown, the test medium that has been used, and all the size and orifice that are qualified under this certification.
Thanks, Bruno. So as you can see, there is the latest one. We passed the test in January 2022, and the certificate is valid until 2028. After that, we need to requalify and to repass national board to redemonstrate our capability to assemble and test such kind of valve. Each certificate, I pick another one. It's the 76 series this time for gas application. The certified value is specific, the 0.848 you see on the comparison API versus ASME presented by Benoit just before. The good point is you can get an access again to any certificate that can issue by any distributor, whether you are manufacturer, distributor, or customer. Anyone has a permission to download this list from National Board, which is an independent third party. You just need to type NB18 in your search bar, and you will have a quick access to this PDF. It will really list out all the manufacturer valve with a performance criteria. So now let's compare briefly the ASME versus API. What's the main difference? So the first difference, if you remember in API, when we talk about the effective section area for the orifice D, we talk about the 0.11 inch square. Here we have the actual flow coefficient. So for the D orifice is 0.124 inch square. It's slightly higher compared to API. If there is different kind of orifice selection, all of them has an actual section area, which is slightly higher API. On the contrary, there is no really valve rating. You can see some connection in net size connection, but that's it. So there is no recommendation as well for the center to phase dimension. And we can understand now one function, the primary function of API, which is to rationalize inlet outlet class per orifice size. It's important. It's important also to note certificate can be updated provided the engineering is able to demonstrate an orifice can reach a higher pressure. For example, here, it's not a typo mistake. If you see a G orifice has a higher set pressure limit compared to the H orifice here, it was simply a demonstration from our engineering. One orifice can reach higher pressure for the needs of for one customer need in the frame of a specific PO. So it's demonstration by a calculation, adopting a forge block. As long as you can demonstrate the body wall thickness is strong enough to withstand the pressure, you can increase the set pressure range of this orifice. So if API standard 526 has been limited, we saw that in terms of material pressure temperature limit, the information we have in ASME are much larger. And the most important, the valve can be a UV stump. In terms of material, it's also the point is on ASP and ASME. API just give you a rough material estimation. There is a 5 material for a spring, 4 material for a pilot, if I remember well. On ASME, you have a large list of material, not as large as we would like. For example, for the nickel alloys, sometimes we have to adopt a bar version instead of casted, because it is not allowed by ASME to adopt the casted version for the 625 or the 825, for example. We need to select alternative nickel alloy. So the material selection is critical, and you need to comply with ASME to stamp the valve. Most of time, any material, so any product, here we have the 2 certificates for the 9 series. Each product has 2 certificates, as explained by Benoit, 1 certificate for gas, 1 certificate for liquid. The code authorized to have 1 valve, 1 certificate for gas and liquid, but it's not going on the right way. It's not going on the way of the efficiency, because if you comply with both, you need to reduce the derivative coefficient factor. So at the end of the day, you increase your shattering risk or such kind of thing, because you increase the oversizing issue. Just to give some color again regarding the benefit of ASME versus API, why you should get out API, we take 2 scenarios. So this one has been highlighted in the previous webinar about the full bore. We just repeat it. So, but if you want to get more detail about the 7th full bore, just be informed there is a separate webinar available on YouTube to know more about full bore. But on that case, we briefly compare some scenarios. So as usual, we have some customer data input here. So set pressure, living temperature, required capacity. We calculate that based on ASME calculation. So if API only accepts to go up to the 8x10 T orifice, the biggest orifice we can select, even with a pilot operated valve, it conducts to have a multiple selection, a multiple valve selection up to 4, as we can see here, versus full bore, where we can select 1 single unit. If you perform any failure mode analysis, you will recognize the highest number of parts or the highest number of components, the higher risk of failure. So if you reduce your quantity, you increase your system reliability, you reduce the risk of failure. So it's also one concern you should have, not only reduce the cost, because at the end, if you have 1 single valve for your application, it's reduced your TCO and your investment, but also in terms of reliability, it's much better. But you need to accept to get out API, because here, as you can see, it's a 10 by 14 inch, so it's out of API. API, it's limited. The biggest size is 8 by 10. One more, and the last one is even sometime when you adopt the pilot technology, finally, it's not enough. In this scenario, we have the customer requirement to protect the production heater. So as usual, we consider all the data, the flow rate, the material has been fixed here, the set pressure, which is quite high, 145 bar, the leaving temperature and the design temperature. So as usual, we have the spring-loaded bar, which is in blue, the pilot operated, which is in green. When it is in gray, it just means you cannot reach the expected set pressure. So basically, this valve cannot be selected. So for the blue bar, for the spring-loaded type, you can see the maximum acceptable size is a key orifice. But if you adopt a key orifice to meet this parameter, capacity plus set pressure, on that case, you need to adopt 7 quantities. On pilot, you can reduce it, but it's still high. And the maximum expected orifice you can go is a P orifice. So as a minimum, you need 2 or 3. On that case, so pilot is the first level, but it's could consider as a level 1. The level 2 is a forge. On forge solution, and on that case, customer really want to adopt a spring-loaded type, because spring-loaded has also a limited number of parts. Sometimes customer is afraid by pilot due to the fitting and tubing that can be brittle. So on that case, he prefer to adopt the spring-loaded robust design, And we can and go on a forge block, the API 6A. So sometimes we have some question regarding the API 6A. Can it be UV stamp? So yes, the answer is yes. We can qualify it. We can demonstrate national board again the capacity of the valve to withstand higher pressure, and on that case to be UV stamp. So we manufacture a valve in the block forge. On that case, it's a special block. It's the set pressure is significantly increased compared to the standard body, the API, the spring-loaded API version. And we can either, instead of 7 3x6 key orifice, we can go either with 3 M orifice, 2 P orifice, or 1 single block forge Q orifice spring-loaded type. It's not fair. Sometimes we have some question regarding the cost, the final cost. It's not fair to compare one casted versus one block forge. No, you have a scenario, a process. We propose solution to match with your process. Basically, here you either need 7 API 526 casted version, spring-loaded type, pressure reserve, or one block forge, spring-loaded type as well, but it's a custom made, it's a bespoke solution. At the end, the cost saving will be proportional. If you go with the M orifice, it's estimated at 25%, P orifice 38%, Q orifice up to 60%. So I don't give you the answer, but I think you understand at the end of the day the choice of the end user regarding the selection you need to adopt for this, for his application. So let's conclude now, and let's summarize what we see together. We saw mainly depending on the project status, it can be feed or firm. You can have relevant, it can be relevant to use API as a preliminary method, sizing method, the preliminary sizing method. However, it will never supersede the ASME law, which is a mandatory for accurate sizing. On a sizing standpoint, you may have to strictly follow API, which is with its standardized dimension and pressure temperature limit. It will offer you the possibility to interchange with another brand for sure, but sometimes it will increase your TCO considering you may have to select a high number of valves. On a performance standpoint, there is no doubt we agree solution can be found to reduce the operational cost, either using forge block that can exceed the API pressure temperature limit, but we still meet some standardized dimension, so it's not completely disconnect. Or you can also adopt the compact design, the full bore pilot operated valve that will have a premium capacity size ratio, and will also limit your TCO. On top of that, if it is recognized at the end of the day, PRV is the most expensive piece of metal you should buy, but you have to buy, but you should never use. In a sense, safety is not supposed to be concerned by performance criteria. In Trillium, we make sure to offer a product that offers premium performance, as demonstrated by Benoit in the following the API standard 527. We not only strictly follow API, we think about the fact in a pilot it can be dangerous to have a lack of leakage, to have a lack of seat force when the pressure is very low, and that's the reason we perform additional testing at 5, 20, 5, 30, and 50%. So that's part of our responsibility to improve your process, especially in a world when finally emission is at the heart of the debate. So we try to reduce the leak as much, any potential source of leakage as much as possible, because if it's not the case today, it will be also part of your responsibility to limit the fugitive emission. Because in the future we can bet we will have some associated fine if due to that. So we arrive at the end of this presentation. again, thank you for your attention. And what I can suggest now is to move on the Q&A session.
For the first question, for boiler steam drum pressure safety valve, should it be 3% or 10% set pressure? I believe you're talking about overpressure. So for ASME section 1 valves that are operating on drums, it's 3% overpressure or 2 psi. The maximum of the two is to consider. But there
Whichever
are
is
some
greater.
but there is some special applications, talking about economizer applications, when they operate only in water, where the overpressure can be raised to 10% overpressure, and you can use ASME VIII certified valve on those kind of specific water applications. So for economizers, it can be 10%, but for steam, it's 3% maximum, or 2 psi.
But for drum, because the question is very specific and it is on the drum side,
it's 3%.
So for steam, it's a 3%.
Yeah.
But yes, it's one of it's ASME update. Now we can use a valve coming from the ASME section 8, so the Starflow, the 9 series, 76, 78, spring and pilot operated valve that can be put in the economizer line if the process is only working on water, only water. One question, if UV stamp is mandatory requirement when buying new PSV, as a UV stamp is usually an additional charge. I tried, if it depends on the country. In US, for sure, you have to apply UV stamp. In the over territory, sometimes customer may decide to not apply the UV stamp, and in that case, you don't have to comply with a UV requirement. I don't know if it's completely an answer your question, because at the end, you talk about charge. Yes, certification is more larger than that. It's more a choice. At the beginning, it was to protect, and it's still a good thing to protect people and equipment. But working on some over territory, we need to pass as a PRV manufacturer additional certification. So in Trillium, we, for example, have the TRCU certificate for the Eurasia, the CELO certificate for China. It's also have a cost. So in terms of cost, it has a direct impact on your competitiveness in the world. So it's more a question of choice. For example, if you go talking about ASME 1, if you compare with in Indian territory for the Indian boiler regulation, it's something we don't want to pass for some strategic reason. We could apply, but we make the choice to not apply because there is no extra charge. If you ask to apply UV stamp or not, the cost is zero. It is back charge on the total production valve and not on one valve specifically. So pilot valve comply with API 526 face-to-face dimension. I don't know if you want to replay, Benoit, or if you let me reply.
I can. In API 526, there are two different tables. The first tables are dealing with spring-loaded valves, and the second part of the API is dealing with pilot-operated valves. So you have some face-to-face dimensions for both kind of valves. We have in Trillium, we have pilot-operated valves that can accommodate either the spring-loaded or the pilot-operated face-to-face dimension. So our pilot-operated valve can be placed instead of a spring-loaded valve, for example, or it can comply with the pilot-operated API face-to-face dimensions.
So it's a good question because sometimes it's misunderstood by EPC customer, and we have such kind of comment in the technical clarification. But yes, we have the real one, the 78 series semi-nozzle type, and we have the one where we adapt the spring, where we use the same casting from spring-loaded. And on that case, it's more a pilot design in compliance with API standard 527 spring loaded table. And we do insist on that because we just want to avoid any confusion here. But a very good question. How to select safety valve type? What are all the conditions to be considered while selection? It's the main criteria for a safety selector valve is also to, in accordance with ASME, is also to comply with the pressure loss, the 3% pressure loss, pressure drop. It means we also design the RS series. We have a RS series, a safety selector valve. So for those who are not familiar, safety selector valve is a product which allow the end user to run the process 24 hours by 7. You can perform maintenance. It's two ways valve, and you can perform maintenance on one valve while the other one is in operation, or you can also increase your capacity, but most of the time it is to select a valve and to isolate the other one performing maintenance. And what we need to take care is the pressure drop, because you are not as close as possible to your process, and sometimes don't match with this 3% pressure drop can lead to oversizing issue for PRV, so it doesn't go on the right way. Fabrizio, is there a standard that indicates the minimum distance between valve and any other device that affects the normal operation of PRV?
This is a good question, because I think you are talking about stepped set pressure when you have multiple valves installed on the same pipe and they are operating at different set pressure levels. API standard 520, you will find some information about the section of the pipe that is required to ensure the inlet pipe will have the correct side, but you don't have any recommendation about the distance between the valves. What I say is the best way to have proper valve operation when you are talking about multiple valves on the same pipe is to
be as close as possible.
Set the valves at the
stagger
most, yes, to stagger it at to keep the maximum pressure difference between the set pressure in order when the first valve is opening, the second one opens the furthest as possible.
Yeah, it's something, a good recommendation is to stagger the valve with a significant percentage difference. Sometimes if you have 7 valves, there is some wrong sizing approach where you stagger it 7 times. You have 7 different kind of set pressure. Is not a good approach. As we said, the set pressure tolerance should be between plus and 3% because it's a mechanical device. You may have some variation because it's a spring material, due to the spring material, due to the internal trim misalignment. The valve trim has to put in place before opening. So, and the valve can keep its closed position for 1 year before operation. So a good practice is to stagger the valve at a percentage which is at least 5% over the set pressure, and you have to multiple valve, but you put 2 of them at the first level and the others at the 5% higher set pressure, and obviously the process won't be oversized.
Okay. Next question is for ASME 1 valves. You have said that the valves are tight up to 96%. However, at what pressure are recommended to work under normal conditions?
96% you can. It will be, of course, as a customer will ask to operate at the highest pressure, because for any boiler manufacturer, the steam is the money maker. So the higher operating pressure, the higher money, and such kind of valve is working on critical condition. So obviously the end user will work at 96%, but it's very complicated.
Yes, my 2 cents on this is that the 96% are the ultimate tightness the valve can reach under laboratory conditions here with our boiler, and it's stable pressure. When you're operating at 96%, for example, you will have some pressure spikes, and then you will start to open the valve, and it will not reclose perfectly if it has not opened fully and reclose at the valve blowdown. So the recommendation would be around 92 to 94% maximum.
Yeah, it's just to avoid to have some opening and closing, and steam pressure is very complicated to stabilize.
And constant leak, because if you have constant leak, you have a very quick wear of the tightness part.
Just we did on this presentation, you can see here a QR code that will drive you to our YouTube page. We already did a webinar regarding the ASME 1 valve, the efficiency, and especially the detail of the technology we use to reach such a kind of high tightness performance. So don't hesitate to scan this QR code to get an access to our YouTube page. Is there any other?
The question is the spring is a weighted part in a conventional safety valve? Yes, on a conventional safety valve, so not bellows balanced safety valve, the spring is considered weighted because it's directly inside the pressure boundary. Whereas when you're talking about a balanced safety valve, the bonnet area is protected by the bellows. So spring is a weighted part.
It also depends. In the oil and gas industry, most of valves are connect. Keep in mind, normally the valve is supposed to be to stay close. So when you speak about weighted parts, you need to consider if you will have back pressure or not. When the valve is relieving, it's weighted part, but normally we consider the weighted part when the valve is normally closed. So it's really a complete approach you need to have if you want to upgrade some material selection due to weighted consideration. If the valve is supposed to keep its closed position and your process is quite stable, in that case you won't have any issue on the spring material and you don't need to upgrade it as in Conner, for example, or such kind of thing.
So final question. Is there a standard that obliges maintenance companies to certify the discharge capacity and not only the set pressure after each valve intervention? For me, the discharge capacity is certified by the valve manufacturer or by the assembler, and it has not to be certified by the maintenance companies. So I don't think there is any standard that obliges the company to certify the discharge capacity. You just have to ensure that the lift of the valve and the orifice diameter is the same as the one written on the nameplate, and the capacity, the sizing of the valve is the responsibility of the first assembler or manufacturer. For me.
Okay. So, again, thanks everyone to join us. And if you have any question, but you can ask directly using our Trillium webpage. You can reach us. Don't hesitate to reach us if you want to know more about API. We are open to discussion. And yes, hope to see you soon for our next webinar. Obviously, it will be in 3 months. We have a lot of content to share about hydrogen fertilizer solution proposed by our engineering department. So it's probably the next one. See you soon.
See you soon. Bye. Thank you to attend this webinar.